Welcome back to the Rocking Reservoir Waves on Rock Physics Driven Machine Learning podcast series. Guests joining us today are Tanya Colwell, Product Manager at Geosoftware, and Jon Downton, Principal Researcher and the geoscientist behind the integrated rock physics driven machine learning workflow technology. In this episode, we will delve in more details of convolutional neural networks and their applications. To recap, for those who may have missed our initial 3 episodes, we explored into the realm of machine learning and its transformative impact on the energy sector. Our focus is on reservoir characterization and the challenges posed by limited well control and the solution offered by using rock physics models to build a synthetic catalog and then using convolutional neural networks for the estimation of reservoir properties. I extend a warm welcome to Tanya and Jon Downton. Thank you both for making time to join our podcast program. How are you doing today?
We're doing well, Joyki. Thank you for inviting us to be a part of this podcast.
Yeah, I'm doing well as well. It's nice to join you in warm Perth while we're up here in Canada in our winter.
It's lovely to have you both today. Jon, I'll start with you. Could you share with our listeners the motivation and inspiration that led to the development of GeoAI technology?
Sure, Yodi. It all started with a Scientific American article that Dan Hampson shared with Brian Russell and myself back in 2016. It was an article written by Yoshua Bengio on deep learning, and he was talking about how it was a revolution. And we took 2 major takeaways from the article. One was that you wanted to have deeper networks. And then the second thing was that with convolutional neural networks, the machine would automatically select the features, which meant you had a lot more automation. And it was really, it drew to our attention how things were changing in the world of machine learning. And Dan and Brian had done a lot of work in the late 1990s on machine learning, and that resulted in the product called Emerge. And it involved different types of neural networks. It had a neural network which actually was very shallow, just a single hidden layer. And from what this article was suggesting, you could get much better results by going deeper. And then the second thing that we took from the article was that within Emerge, you have to go in, and a big part of the workflow is generating attributes and then selecting these attributes in order to get featured or to make the predictions. And the article suggested this could all be done automatically. And so this took us down the road to starting to look at these deep neural networks. And at that point in time, I went ahead and coded a fully connected deep neural network and put that in Emerge. And we saw that it gave really nice results. And so we were impressed with it. It did as good as what we could see out of PNN, and it was much faster. But there was some issues in terms of the amount of data, like in terms of picking hyperparameters, in terms of the stability of those hyperparameters. And I'll return to that a little bit later on and talk more about those observations.
Thank you, Jon. Thank you so much for sharing the background and the motivation behind the new technology. Tanya, considering the current timeline and the prevalence of deep learning algorithms, our technology aligns impeccably with the technological landscape. I wonder, was it a pre-thought strategy, or did it naturally evolve in response to the emerging opportunities in deep learning?
Jon pointed out Geosoftware, Hampson Russell specifically, has been developing neural network since late 90s in emerge. So we wanted to continue develop this field. So in a sense, we recognize the potential early on, and also our approach evolved organically in response to emerging opportunities. And so it's almost like a balance of staying ahead of the curve and responding to the market interests. And so there is definitely a big market interest in deep learning. So it was, in a sense, it was a response to that as well.
Lovely. Jon, let me come back to you. Can you please provide some insight on why you chose rock physics modeling approach rather than conventional simulation for generating data catalog for deep learning? I wondered what were the factors that influenced the development directions.
So one of the themes at the time also was around big data. If you look at all the large computer companies like Google, they're accessing large data sets in order to train their deep neural networks. And when we first tried just playing with deeper, fully connected networks, we saw that there was stability issues related to choosing optimal hyperparameters. And one of the issues we like to think of geophysics when we're working with seismic data to have big data, but the issue we have is we don't have much supervised data or much training data. The training data is coming from the well data. We have all sorts of tricks to try and improve that training data so we have enough information so the machine can learn the relationships. But we've always struggled with having enough information to train the neural network. So in the computing science field, they do all sorts of things with their images to try and increase the amount of data. So they'll do rotation, they'll change the width, the height, they'll do shear transformations, they'll zoom. And one thing we could do is if we take the input petrophysical curves in, we can do simple transformations with which interpreters do all the time. We can change the thickness and do tuning studies on a reservoir, and we can see how does that change the character. We can, let's say, do fluid substitution where we change the saturation. So it's sort of like changing the height in an image, or it's changing or doing some sort of shear motion in the image. And so we can create many different types of images to increase the amount of data that we're bringing in. And so we found that to be quite a powerful way of increasing the amount of data and improving or allowing the network to learn very similar to how an interpreter might learn in their modeling studies to learn how the character is going to change if you change certain variables.
Thank you for sharing that perspective, Jon. Now turning to Tanya. Tanya, we often receive a common question from our users that after generating a synthetic catalog, are we then aiming to identify the AVIO signatures of those various scenarios within our seismic data? And does the location of these synthetic wells hold any significance for us in this entire process?
So once we generate a synthetic catalog, we have a series of possibilities that are representative of our data set. So in our case, this synthetic catalog isn't locked to a specific X and Y coordinates. You can think of it as a pseudo representation of all 3D responses, representation of different seismograms that can happen for your geological situation. So our goal was not to compare one specific response and to try to identify it within the seismic data. Our goal was to create a well-balanced data set with various variations. However, it is possible to develop the software. You can apply also other techniques such as Monte Carlo simulations or systematic changes, apply those changes on your wells and develop a program that directly studies the response in your seismic gather.
Right, Tanya, thank you. Jon, another question that often arises is the choice of convolutional neural network. I wonder if there is any specific advantage in using CNN in comparison to other neural network architectures?
Well, going back to that article by Bengio, he mentioned two advantages. One was the depth of the network, and the other one was the machine picking the features. So if you're using a convolutional network, it's essentially doing two-dimensional or higher dimensional convolutions, and it's going to look, or it's going to try and extract features, or you could also think of them like attributes, and the machine is going to do this and come up with an optimal choice of this. And one of the requests that we always had regarding a merge was that people, it can be quite labor intensive to go through, select the features, and then make predictions for a specific target. And if you want to go through and estimate multiple targets, let's say you want to do the saturation, the porosity, the V clay, that involves going through the workflow 3 different times. And by the machine picking the features, you can come up with optimal features for each one of those targets and then make the predictions. And I think that gives rise to a much more efficient workflow. And I think that's one of the big benefits of making use of the convolutional neural networks.
I think you mentioned that in your earlier podcasts, that one of the benefits of this approach is that we can predict multiple targets, multiple reservoir properties with one training model. So we can predict P impedance, S impedance, density, porosity, and V clay, while there is only one training model that's derived for this data set.
One other thing that comes to mind is that with convolutional neural networks, you can also do transfer learning. And we found that to be a real powerful concept because, again, you can train on different data sets and then update it with other information. We're using that first to train on the synthetic and then to incorporate the real well logs, and it allows you to incorporate or take into account systematic issues in terms of the modeling when we do when we generate the synthetic gathers.
Perfect. Tanya and Jon, when we look at CNN results, now that we know that why we have chosen CNN, when we look at the results, we often observe a better resolution compared to seismic data. I would like to know where these additional details are coming from, and will it be always the case? Tanya, would you like to answer this question?
Well, we can always speculate where the resolution is coming from. So one of the possibilities is that the network can see the nonlinear relationships that are not picked up by the traditional pre-stack deterministic inversion. So another additional detail comes from the training data set. So again, if you have a well-balanced data set that covers all the possible variations, and yet these variations are within the geological bounds, so they're limited by the rock physics. So that's where the additional resolution comes from. But from what we see in our tests, in our projects that we do, the results are typically better than the traditional deterministic inversion.
Thank you, Tanya. Yes, John, you want to add in something?
I was just going to add it and put it maybe a little bit different way, in that when we're doing deterministic conversion, our objective function is minimizing the difference between our predicted model and which is the predicted seismic versus the seismic, and it's band limited. When we're trying to do supervised learning, we're predicting from the seismic data to the well data, and our well log data, it's not band limited, and in the learning process we're also going to carry some extra prior information along with it. And I think it's the same thing Tanya is, but I suspect what's going on is that we're carrying some of this prior information in through the learning process, and I think that's what's giving us the higher frequency that we can observe.
Thank you, John, for adding in your perspective. Now coming to the context of convolutional neural network and other neural network architectures, I wonder what are some challenges and considerations when deploying pre-trained models to completely new data sets. In fact, this is particularly relevant given the rise of pre-trained model these days.
That is absolutely true. We do see the emergence of pre-trained models on the market. We have to be very cautious in applying the pre-trained models blindly. It would be good if all the assumptions on how these models were created, if they are revealed, specifically what parameters were used, what geological settings, so they cannot be applied as a blind box. John, would you like to add something?
Yeah, I guess the thing I'm thinking about is that rock physics models are often non-unique. You can get the same seismic response from different sets of parameters going in. And locally, they're often unique. You can say that you can exclude certain situations. So the thing to keep in mind, I think, is that the mapping between petroelastic parameters and seismic is non-unique, but maybe over a certain set of geology, like maybe a certain depth range, maybe for specific facies, maybe for certain fluids, you can say that mapping is unique. Some other things that go into it that I think you need to update is that, for instance, we're working with pre-stacked data, so the angle range that you're working with will change how you're going to do the learning. And the wavelet, like in terms of the frequency content that you have available and the type of wavelet, again, that will make it very specific. So I think we can train in a generic sense, but maybe you can do transfer learning to try and update it. But going back to the geology, I think you have to look at a particular set of geology and train for that if you're going to be trying to make estimates of petroelastic parameters. We've had some experience where people have trained for one particular 3D, and then they've been able to apply that network to other 3Ds within the area. And so we think doing that is reasonable. I don't know if you could train, let's say, in one geologic basin and move to another area. And I would go back to, I think a lot of transforms in geophysics are non-unique, and we always have to recognize that. And machine learning is going to have the same limitations.
Also, in the exploration type settings, when they have a very limited number of wells, right? What they can do, they can train on the areas that has been previously developed and transfer that pre-trained model on the areas, speculating that you are still within the same geological environment.
talking about the geological environment, that brings another question in my mind. How's your experience with the technology across various geological settings? I am sure our listeners would like to hear your confidence in the technology across different geological settings.
We have done a number of projects with our clients so far in some types of carbonates, in unconventionals. So currently we are also targeting geothermal type applications and actively kind of responding to the client requests and the challenges that rise to these during these projects. And we consistently see good results, good predictions. As we mentioned before, they are very comparable to deterministic inversion or better than deterministic inversion. They are comparable to emerge and DFNN like approach. So we have a good confidence in this technology. It is also becoming a very mature product. So it's well tested and has been applied by a few projects, quite a few projects worldwide.
Thank you, Tanya. And now, in terms of predictions, do you think that with given project timeline and requirement, GeoAI technology can provide desired predictions for static modeling like water saturation, volume of clay, and porosity?
Many of the projects we're doing, we're trying to predict things like the water saturation, the mineralogy such as B clay and porosity, and we've seen that it works quite well. In fact, like if you can go back to emerge, that was one of the real interesting things about emerge, is people used to do it to try and predict for these different properties, and so I think there's quite a proven track record in predicting these. Some of the work that we've done recently is we've been looking at transfer learning and the impact of using different wells on the predictions. And by doing multiple predictions, we can see the variations in these predictions for the different properties. And it gives us some understanding of the range of values and an idea of the uncertainty associated with it. Some of the parameters, depending upon the physics of the problem, are going to be better predicted than others. For example, porosity. We have quite a bit of experience predicting porosity using seismic. Saturation is a more challenging but again, in a broad sense, we can often say something about the whether it's more hydrocarbon filled or water or brine filled. And V clay, we can do a reasonable job there. But again, it really depends upon the rock physics that you have and how well resolved those parameters are. And by looking at some of the uncertainty analysis, you can get a sense of that, of the uncertainty and the resolution of that particular parameter you're trying to estimate.
Thank you, John. One last question. I would like to get your perspective on the future of theory-guided machine learning methods. Do you anticipate more research in this domain?
Well, one thing we've been looking, actually both Tanya and I can answer this, but one thing we've been doing throughout our research is we've been looking at trying to estimate continuous properties and also categorical properties. Like if you look at convolutional networks, many people are trying to predict categorical variables such as facies. And we've done some work on that, but most of our focus has been on continuous properties such as porosity, saturation, or mineralogy. And so we're going to spend more time looking at categorical properties, and then maybe also in combination. And can we make use of, let's say, the facies to help improve are predictions of the continuous variables as well. So there's certain architectures that you could look at, similar, let's say a FASIS-driven inversion. You could probably bring those concepts in as well.
Another area that we are looking into is changing the approach of convolutional neural networks and making it simpler to use or to apply those networks. So currently we are going through the workflow from petroelastic parameters to elastic parameters, then to synthetic catalog. So there is a big dependency on the rock physics component there. And as we know, rock physics is a complicated subject, and especially in certain type of environment, it's difficult to derive a good rock physics model. There are quite variations there that we can play with. We are trying to simplify the workflow so it does not rely on the rock physics. We can start with elastic properties and compute synthetic catalog from elastic properties, and that way we remove the dependency on the rock physics. So we are looking into ways of how we can make the product more accessible, perhaps to generalists, and have this workflow more repeatable and easier to run.
And just as important, one of the interesting things, we're running into clients now who have hundreds of wells in a data set. And so the question is can we just take those hundreds of wells, and is that sufficient to go off and train? And then that allows us to go with a simpler workflow as well.
Thank you so much. I must say that your insights on rock physics-driven machine learning for seismic reservoir characterization has enriched our discussion. We appreciate your significant contribution in this breakthrough technology, and we look forward to hearing more from both of you in the near future. Thank you so much for your time. And with that, we have reached the finale of Rocking Reservoir Waves on Rock Physics-Driven Machine Learning podcast series. This podcast series has taken our listeners on a journey to understand how we can integrate machine learning with theory-based methods to derive quick and better subsurface reservoir characterization. The technology is indeed very helpful, especially in the exploration field, where data limitation is a big hindrance for using machine learning methods. This finale episode is indeed an icing on the cake in our podcast series, and we look forward to more such interactions. So whether you are a geophysicist, petrophysicist, engineer, geoscientist, data analyst, or simply a curious mind, keep following our podcast channel, as through the journey, you will learn the captivating world of rock physics-driven machine learning on our Rocking Reservoir Waves channel. So if you have questions or topics you would like us to cover, feel free to reach out via our website or social media channels. Until then, keep exploring, keep questioning, and keep rocking.